All right, we've reached a point now where we've gone through the first two steps of a test hypothesis. We've set up the test by specifying the null and the alternative hypothesis, and we've gone out and we've collected some data. And the data we've collected have been put into a formula, and we've got a number. And now the question becomes, how do we evaluate that test statistic? How do we know what that test statistic is saying? Remember, the test is set up so that if the null hypothesis is true, we know what the test statistic should look like. In other words, we know the sampling distribution. Um, is it a z? Is it a t? Is it a chi-squared or is it an f? We'll know which one of those it is, and because we know which one it is, we know what to expect. And so let me go here. The rejection regions, there's actually two ways of doing this. There's rejection regions, and there's another technique that I'll come back later and talk about called the p-value method. The rejection regions is the method that makes the most sense now based upon what you've done recently with sampling distribution. So the rejection regions give values of the test statistic that are unexpected and lead us to reject H naught. Listen to the name. It's called a rejection region. It's a region of the curve that allows us to reject. You see in your notes here, I say it's based on the sampling distribution of the test, the direction of the test, and our choice of the alpha of our error. The sampling distribution, is it a z, t, chi-squared, f, things you'll see later. For the most part, when I'm having this conversation with you initially, it's T's and Z's. That's a sample size question. Are we working with large samples or are we working with small samples? The direction of the test, the alternative hypothesis allows for, in a lot of cases, not in all, but in a lot of cases, it allows for three different directions: greater than, less than, and not equal to. Depending what you're trying to say. Are you trying to say a mean is greater than some number? Are you trying to say a proportion is less than some number? Or are you just trying to show a not equal to, a two-tailed? We refer to these tests as one-tailed and two-tailed test because it indicates to us, the direction of the test indicates where we're looking at in the curve. And then the third thing is our choice of alpha. As our alpha gets bigger, that's going to have an impact. And so you see the first example here, and I'm going to draw a little curve. And that pen's a little bit thicker than I was hoping for. Let me see if I can change that. Let's see if I can do this. Yeah, I can probably do that. All right, so here's, let's say we have, in this first example, let's say we have a z distribution. I'm assuming that we have a large sample. That's why I'm calling the test statistic a z. What we're going to do is take our 0.05 and put it all in the upper tail of the curve. Why would we do that? Because this rejection region would work if we had a greater than test. And I'm not going to put a parameter, I'm not going to put a value because mu greater than 700, p greater than 0.4. When we get to comparing two means, mu1 minus mu2 greater than 0. Anytime you have a greater than test, you're going to go and look in the upper tail. Now, if this is the case, and I went to the z distribution because I had a large sample, this value is 1.645. What this rejection region says is, if the null hypothesis is true, we should see some test statistic over here. We won't expect to see a test statistic out there. And the logic goes, well, if you see a test statistic out there, that's very unlikely. So unlikely that we're going to reject the null hypothesis. So the rejection region is a rule for when the null hypothesis should be rejected. I'll give you another example here. At alpha equal 0.05, we're going to reject if t is greater than 1.2, or excuse me, 2.145 or negative, less than negative 2.145. If you have an n of 15, we're not going to use a z distribution. We would use a crazy looking t. Sorry about that. I'm writing with a mouse though. Give me some grace. With 14 and minus 1 degrees of freedom. If you have a not equal to test, and I'll change the ink color here. I'll go to red now. We're going to take our 0.05, and because it's a not equal to test, we're going to put half of it out here. So this will be 0.025. And we're going to put the other half in the other tail. So there's going to be a 0.025 in the lower tail as well. We split the alpha when we have a not equal to. This is kind of what we've done with confidence intervals. We always took our alphas and split it. A t distribution is also centered at 0, but now you're going to go to the t table. You're going to go to 14 degrees of freedom. You're going to go to 0.025 column, and you're going to see a 2.145. And that's a 1 there. It looks almost like a 6. That should be a 1. And a negative 2.145. If the null hypothesis is true, we would expect to see a test statistic between these two numbers. we would expect to see a test statistic in here. That would be what's expected between those cutoff points. If you see a test statistic out here or out here, that would be, excuse me, unexpected. And that would lead us to reject H0. And so we're going to write the rejection region this way at alpha equal 0.05 in this case. We'd reject if t is greater than 2.145 or less than negative 2.145. The rejection region always requires us to use a statistical table. Early in the semester, there's Z's and T's. Later in the semester, chi-squareds and F's. And as I mentioned, there's another way of doing all this. It's called the p-value approach, and we'll get to that later. But that's going to be one way to allow us to kind of downplay the sampling distributions and let the computer do some of the work for us. So I'll show you that later. But that's how you evaluate a test statistic with a rejection region. The next step is to work with a conclusion. And I'll come back in the next video and talk about conclusions. So long.